Hello, my name is Jake McNaughton. I want to give a brief summary of the highlights of our work, Adaptive Neural Quantum States, a Recurrent Neural Network Perspective. Neural quantum states are a compressed representation of wave functions as a neural network. Many different machine learning architectures have been used as neural quantum states, including feed-forward neural networks, convolutional neural networks, transformers, and in particular, recurrent neural networks, which is what we will look at here. Neural quantum states are optimized through the variational principle, which states that the expectation value of the Hamiltonian with any trial wave function is bounded below by the ground state energy. By varying a parameterized wave function until the expectation value is minimized, we can therefore approximate the ground state wave function. Stochastic Hamiltonians are a special class of Hamiltonians where the amplitudes are real and positive, and the wave function can therefore be given by the square root of the probability distribution that is provided by the RNN. Neural networks, however, suffer from the curse of dimensionality. So although neural quantum states can be systematically improved by increasing the number of parameters, larger models require increasingly large amounts of computational resources. Here we propose training a series of RNNs, benefiting from the fast, simple nature of small models early on in training, and progressing through a sequence of increasingly large models by transferring parameters from the previous model. At each point when we change models, we initialize a new model with larger parameters, and then embed the parameters from the previous model into these larger initialized parameters. Here is a diagram of the scheme we use when we look at the one-dimensional Ising model with nearest neighbor interactions. We term the standard process of training one RNN with a fixed hidden dimension, a static RNN. In this case, we train a static RNN through 50,000 training steps with a hidden dimension and model dimension of 256. On the other hand, for the adaptive RNN, we begin with a hidden dimension of 2, and we double it at fixed intervals up until we reach 256. Here are the results. So on the left-hand side, we can see the results for the one-dimensional transverse failed Ising model with nearest neighbor interactions. We can see that the adaptive RNN from halfway through training, in terms of the number of training steps, reaches on average lower variances. Here we're looking at the variance per spin. So an average lower variance as well as less deviation in the variances. By looking at the inset on the top right, we can see that the training finishes in approximately a third of the time it takes to train a static RNN, and that at each point the adaptive RNN has lower variances when we consider in time, even early on in training. On the right-hand side, we can see the results for the two-dimensional Heisenberg model. Here we train a static RNN and adaptive RNN, and we also implement a new protocol for changing the adaptive RNN, which we call the adaptive RNN with early stopping. This is where we use an early stopping criterion to decide when to change over models rather than changing them at fixed intervals. We can see here, again, the adaptive RNN finishes in about a third of the time, but the adaptive RNN with early stopping does not gain much of a time advantage. However, both adaptive RNNs reach lower variances than the static RNN. Additionally, we trialed two more Hamiltonians. On the left, we can see the one-dimensional Ising model, this time with long-range interactions. And on the right-hand side, we can see a rotated cluster state. In both cases, we see the adaptive RNN converging slower in the first part of training in terms of the number of training steps, but in the end converging to lower energies. Initially, when we looked at the one-dimensional Ising model with nearest neighbor connections, it was for 100 spins. Here are the results for the other lattice sizes we looked at, 20, 40, 60, and 80. We can see in each case the average variance that the adaptive RNN converges to is generally lower than the static one with less deviation, and that there is more stability in the adaptive RNN. We can compare the time difference between the adaptive and static methods for a one-dimensional Ising model as a function of system size. Here we can see that as the system size increases, we get a more noticeable time difference. These This takes the form of a quadratic, and we can look at what the ratio between adaptive and static models tends to as the system size increases about bound. We have found that this increases to approximately 34%. In conclusion, the adaptive scheme provides us with lower energies, improved accuracies, increased stability, and a reduction in training time, and therefore computational resources used. There are multiple future directions that this research could be taken in, including looking at optimal changing criterion. For example, the early stopping criterion used was not optimal as it didn't perform as well as change at fixed intervals, but there might be a more optimal way to change over the model to determine when this changeover should occur. Also, it would be interesting to apply this scheme of training, increasing model size throughout training, to different architectures for neural quantum states, as well as for different neural network applications in machine learning. Thank you very much. I would encourage you to look at our preprint as well as our code, which is available on GitHub by scanning the QR codes on the bottom.